My title of my talk is Mathematics in Medieval Islam on its Own Terms. And I want to talk to you about the kinds of things we can learn when we approach the mathematics of medieval Islam on its own terms and not on terms that we choose. It has been sometimes in the past a tendency to treat mathematics in medieval Islam as if its principal achievement was to preserve the mathematics of the Greeks and pass it on to the eager minds of the European Renaissance, and that has been more or less the debt we owe to medieval Islam. Now, we all know, I'm sure everyone in this room knows, and many people in the West know, that we got, the Hindu-Arabic numerals. So Islam was responsible for bringing us the Hindu-Arabic numerals, and usually that story ends there about numeration in medieval Islam. But the story is much more interesting and much richer than that when you begin to try to understand the mathematics in its own terms, which is the theme of my talk. And the three different kinds of calculation. One was the arithmetic of the hand, hisab al-yad, which was not counting on your fingers, but it was using mental arithmetic to carry on computations, and intermediate results were sort of stored on these storage registers here on your hands, and the fingers were held in certain positions to indicate numbers up to 1,000. Okay, so you might write the number out, the whole number out in the Hindi numerals, but then when you came to fractions, you'd switch bases from 10 to 60, and you would treat it as if it was degrees, minutes, and seconds. And so and Ibn Tahir al-Baghdadi, in the 11th century, when he wrote his compendium on reckoning, included hand reckoning and the base 60 system, along with the decimal system of the Hindus. In fact, not only did reckoning include these three systems, it also included algebra. And the very eminent professor at Harvard, Abdul Hamid Sabra, wrote in his article on Hisab in the Encyclopedia of Islam that many books which were called Hisab were in fact books on algebra. And you can kind of understand why that might be, because after all, what is arithmetic about? It's computing things. And, well, whether you know what you're computing or you don't know what you're computing, in other words, the unknown, it's still a matter of computing. And so that's, I think, how algebra became, at least in the medieval terms, part of Hisab. So it was really only until about, I would say about the 14th century that the Hisab al-Yad began to drop out, and you don't find it mentioned in the books. And in fact, some of the theorems that one would find there are this kind of thing. The identities for the signs of sums and differences of angles, which would be a great aid in constructing trigonometric tables. The law of sines, which was both for plane and spherical triangles, and that much simplified the task of surveyors and astronomers in calculating unknown parts of triangles from the known parts of the triangles. And the third, methods of computing trigonometric tables to arbitrary accuracy. And in fact, it's interesting to look at the accuracy to which these tables were computed as the years went on. Around the year 900, al-Battani gave a table in his book on astronomy of the sine function at intervals of half a degree to 3 places of accuracy. 130 years later, al-Biruni gave tables of the sine and tangent functions to steps of 1/4 of a degree for the sine function and 1 degree for the tangent function. and to 4 places of accuracy. And then by 1440, Ulugh Beg, the king or the ruler, the prince of Samarkand, computed these tables of the sine steps of 1 minute. Okay, 1 minute, 60 in a degree, 90 degrees to a quadrant. Okay, 60 times 90, 5,400 5,400 computations, right? Carried out to 5 places of accuracy. So these are remarkable computational achievements, and it seems almost incredible that people could have done this when there was there were no really computing devices of the sort that we're used to. But he didn't earn his living as a mathematician. That's what I'm saying. Al-Karaji, who discovered the binomial theorem in algebra. Al-Karaji was an engineer. Nasruddin Tusi, I had mentioned, who invented trigonometry, was an astronomer. Jamshid al-Kashi was an astronomer. Most of these people were supported by the wealthy, either the rulers or prominent families, or undertook particular jobs in the cases of engineers and so on. So this was, you just can go through the list of people who were mathematicians, or we'd say were mathematicians, and you'd find really they were earning their living doing something else. Teachers, that was one way you could earn a living working in mathematics. You could become a tutor. There was not a lot of mathematics taught at the basic school level. The idea there was that you would learn the elements of Arabic so that you could read the Quran properly and understand what you were reading. And there was also the idea that you could go on to the madrasa, and there were madrasas, and they had very intelligent faculty and very learned people, but they were focused more on the religious sciences than on the foreign sciences as the sciences obtained from the Greeks and the Persians and the Hindus and so on were called. And so there was not a lot of formal instruction, but if you wanted to learn advanced mathematics, you hired a tutor. And tutors, in fact, were a common way of learning advanced mathematics. In fact, one of the things that came out of the teaching of mathematics, and this was especially in the Maghrib, was the introduction of mathematical symbols in writing mathematical texts. So, for example, the shin for shay, the thing, the unknown, okay? Or mim for mal, property, or it came to mean the square of the unknown. Kaf for kab, okay, the cube, okay. Jim for jither, the root, the square root, okay. And li for equals, musawi li. And so the lamb was simply for the equal sign. So this developed out of the pedagogical environment in the Maghreb, especially in Morocco, but in nearby countries there too. The mathematicians tried to answer some of these charges in various ways. I mean, the idea was to show that mathematics at an advanced level was important to the Muslim community. And so Ibn Khaldun remarks in his Muqaddimah, he says, talking about the law of inheritance, which, of course, one does involve mathematics. I mean, going back to Al-Khwarizmi in the 9th century, his book on algebra includes a number of inheritance problems. And he shows how to use algebra to solve the inheritance problems. So, but Ibn Khaldun says, religious scholars in the Muslim cities have paid much attention to it, the laws of inheritance. Some authors are inclined to exaggerate the mathematical side and to pose problems requiring for their solution various branches of arithmetic, such as algebra, the use of roots, and similar things. It is of no practical use in inheritance matters because it deals with unusual and rare cases. So now, there were also cartographic solutions to religious problems, such as finding the direction of Mecca. One of these, the three things I wanted to discuss, the noons, the prayers, and the direction of Mecca. This was an interesting early map here. It's a rectangular projection. It represents some of the cities of the Muslim world. I think you can see here Mecca, okay? And they're saying that, okay, take a city such as Isfahan, and then just draw a line joining Isfahan to Mecca, and read off the angle to the meridian, and that will give you the direction of Mecca from Isfahan. Well, it would if the earth were flat, but the earth isn't flat. It's certainly a reasonable approximation if you're somewhere not too far from Mecca, okay? But once you get into Central Asia, Samarkand and so on, this is not going to be accurate. But that was the illustration you see here for Mecca, Isfahan, and it says, okay, there's the number of degrees for the Qibla. Okay. Now, there were much more sophisticated solutions than this that were developed, and I just want to show you another one here. This was a remarkable device. This is one of those devices that if it had not been found, nobody would believe that it existed. It was made in the 17th century in Iran. It is suspected, David King suspects that in fact it actually goes back much earlier than this to the 10th century in Baghdad. But that's his speculation on this. So what it is the following. You've got lines of longitude here. You have lines of latitude here. And in each little square, I think these are 2-degree steps of longitude and latitude, okay, there is written the name of some city who is located at that longitude and latitude. And to find the Qibla, what you do is you rotate this ruler until the edge passes through the particular city where you live, okay? And then you can read off from the degrees there, you can read off what is the Qibla of Mecca. And this is accurate. Okay? It requires no computation whatever. It requires no tables whatever. The work is all done in the mathematical projection of the longitude and latitude lines. Now, as I say, it never rains, it pours. Since they found the first one, they found 2 more. The third one was found sitting in the basement at Harvard University. Nobody knew it was there. But these devices were developed. Some person who developed it was a genius. I mean, this mathematical projection, it's quite remarkable. I think, anyway, what I mean by looking at medieval Islamic mathematics in its own terms, I will hope you will find something within the lecture, both in terms of what those terms were and what the achievements of the resulting mathematics was that justifies your presence here today. And thank you for your attention.